My name is David Powlin, and today we're going to have some fun with these squares and cubes and nets. And we're going to be looking at four-dimensional hypercubes. And well, we can't really look at four-dimensional hypercubes, but we can look at three-dimensional nets of four-dimensional hypercubes. A four-dimensional cube would have a fourth dimension that is perpendicular to our three dimensions. So we have one dimension across this way, we got one dimension across this way, and we got one dimension across this way. And a fourth dimension, all three of these dimensions are perpendicular to each other. A fourth dimension would have to be perpendicular to these three dimensions. We can't get a physical sense of that. I mean, it's just impossible. But we can visualize if a four cube was unfolded into a net, what it would look like in three dimensions. Just as if we unfolded one of these cubes, it would look like our very familiar two-dimensional net. So that's what we're going to do to get started. We're going to actually go back and use some of our prior knowledge of two-dimensional nets of three cubes to take it a step forward and try to visualize and to actually construct a three cube from a four-dimensional hypercube. So, the two-dimensional net very easily folds up. If you gave this to an elementary school child, even they would probably know how to fold this into a cube, or they could quickly understand and learn how to do it. And you could just fold up each one of these edges, of course, and it creates one of our three cubes, correct? And it's got six faces. Now, it's important to understand, and we did some analysis of the faces and edges of cubes and three cubes and four cubes, and we do understand from our analysis that our four cube is going to have 8 cubes in it. It's going to have 8 cubes in it, just as our three cube has 1, 2, 3, 4, 5, 6 faces, and they're going to fold up like this. Now, taking another step backwards, and I'm going to be using these line segments over here in a second, but taking another step backwards, now imagine we're trying to explain this two-dimensional net to a two-dimensional creature. And this two-dimensional creature lives on the surface of this desk, and we're trying to explain to them that there is such a thing, or they're trying to explain, their mathematicians are trying to explain to, two-dimensional mathematicians are trying to explain to each other what a three cube would look like. And the problem is if I am trying to explain this to them, I might say, well, look, it's very simple. You just fold these down, and they're going to say, fold what down? Because they cannot see, the two-dimensional creatures cannot see any of this stuff coming up from the edges, so that's going to get nowhere. But if we even go one step back, more backwards for them, one step back, say, well, remember if you have a square is really a two cube. And if you unfold a square, it folds into 4 line segments, and you could build it a different way. Okay, they could see it like this. Well, here is a two-dimensional net, right? Or a two-dimensional. Well, I guess it would be one-dimensional if we went like this. A one-dimensional net of a square, or of a two cube. And to create the square, they understand, they could visualize, and they could see that you just fold each edge on a vertex. So you fold the edge on a vertex. In the same way, when we move up one dimension, we fold each face on an edge. So here we got an edge folded on a vertex, move up to the next dimension, and each edge is folded on each face is folded on an edge until you create the cube, or folded down until you create the net. Now, they couldn't see that folding at best if we cut out each one of these faces. So just quickly cut these out here. 1, 2, 3, 4, 5, 6 squares, or 6 faces. So the best the two-dimensional creatures could get a sense of this net of the 3 cube is each face then is, instead of folding for them, each face would be pulling out of an edge. Okay, each face would be pulling out of an edge, like so, until you finally end up with your net of the 3 cube. And that's the best that a two-dimensional creature could come to understanding what a net of a 3 cube would look like. Each face would pull out of an edge like this. So we, going back one more time, we got with the square, we got edges folding on vertex. With the cube, we got faces folding on the edge to the two-dimensional creatures. They're pulling out. Now, us going up to the next step, the 4 cube is made up of 8 cubes, and each cube pulls out of a face. So here I have a face, and I got to pull a cube out of the face. Now, just as it doesn't make that much sense for the creature to imagine, they just have to mathematically imagine that that's happening. We very well understand what's happening. But the cube would pull out of the face, and then you would have these two folded together. And then on the other side, I could pull another cube out of another face. And now I have 3 cubes. And then I could pull another cube out of a face, maybe this way. And I could pull another cube out of a face, maybe this way. And I would just have to keep pulling cubes out of faces. I'm going to turn this over so I can reinforce it a bit. So I would keep pulling cubes out of faces until I've pulled out all 8 cubes. And that would be my 3-dimensional net of a 4 cube. So we're building it up. We've got to pull out a couple more cubes. We're getting there. Pull one out this way. We are going to have to pull out one more on top, just like on the 2-dimensional net. There's got to be one more pulled up top there to close everything in. So something has to get closed in on that 4-dimensional net. I guess we could say God only knows how that happens, or 4-dimensional creatures, whatever it is in that space. And then one more on the other side. And voila! We have our 3-dimensional representation, a 3-dimensional net of a 4 cube. And didn't come out too bad. I've seen worse. Thank you very much. And that's all.